second squared? Acceleration. Yes. So, let's see how this is related. The force experienced by a unit mass placed at a height h above the surface of the earth. Can you write down that equation? What is the equation for the force experienced by a unit mass placed at a height h above the surface of the earth? Well, this is the equation for the force experienced by an object placed on the surface of the earth where h is 0. We say the force of gravity on a mass of 1 kilogram. Now, if you remember, this is our original equation. If you place an object on the surface of the earth, the force of gravity on it will be F equal to g times mass of the earth times mass of the object divided by the square of the radius. So remember, we are not placing the object at a height h, we are placing the object on the surface of the earth where the distance between the center of the earth and the object is the radius. Well, since gravitational field is the force per unit mass, then what is the value of this m? That will be 1. When this m equal to 1, you can see the force per unit mass is gme over re squared. And this is a measure of the gravitational force on the surface of the earth. If you now want to find the gravitational field at an altitude h, replace this Re by Re plus h. Is that right? Yes. So the force field at a distance h will then be gme over Re plus h all squared. So if this is the gravitational field on the surface of the earth, this quantity where m equal to 1, then this will represent the gravitational field at a height h above the surface. Alright? And this is equal to g, is that right? Because gme over re squared is what is called acceleration due to gravity. And therefore, this is a very interesting phenomenon. The gravitational field at a point is simply a measure of the acceleration due to gravity at that point. You see how the unit is now meter per second squared agrees with this definition? So the gravitational field at a point is a measure of the acceleration due to gravity at that point. Now, gravitational field can be represented by vector notation as Fg equal to negative Gj. Now, did you understand this? Gravitational field is a vector that is directed towards the earth. Anything that is directed downward is a y vector. Anything that is directed in the vertical direction is a y vector. And since the gravitational field is directed towards the earth, it is directed downwards, it is a negative vector. The gravitational field is a measure of g at any point. And you can see as we move away from the earth, the value of g will become smaller and smaller. That means the magnitude of this vector will become smaller. Where is the magnitude of this vector the greatest? The magnitude of this vector is the greatest at the surface of the earth. So look at the vectors that I have drawn at various points. If you want to draw the gravitational field vector here, it is this arrow, negative g. Whereas the gravitational field at a point nearer to the surface of the earth is represented by a longer arrow. the length of the arrow represents the magnitude of the field. So as you go away, the length of the arrow becomes smaller and smaller, indicating that the value of G is becoming smaller and smaller. The gravitational force field becoming weaker and weaker as we go away from the surface of the Earth. Now, will there be a point where the gravitational force field due to the Earth is absolutely zero? Well, for practical purposes, we can say the gravitational force field at infinity, at an infinite distance from the Earth, will be zero. All right. So the unit of gravitational field is, we talked about it, it is Newton per kilogram, which is the same as meter per second squared. Okay. Let's do a small problem. What is the gravitational field at a point where the weight of an object is 3 kilograms? The weight of a 3 kilogram object is negative 15 Newton J. Now, if you understood the concept I described, you can give me the answer right away. Gravitational field is the force per unit mass. Now, the weight of a 3 kilogram object is negative 15 Newton, means that is the force on the 3 kilogram there. Therefore, if you place 1 kilogram, what will be the force? If this is the force experienced by the 3 kilogram object, what will be the force experienced by 1 kilogram object? Gravitational field at a point is force per unit mass. Therefore, the gravitational field at that particular point will be the force divided by the mass, force per unit mass. That will be negative 5 Newton per kilogram J. That will be negative 5 meter per second squared J. Is that right? It's at a very far distance from the Earth. Let's now talk about orbital speed of a satellite. What is the meaning of orbital speed? If I can throw this basketball with sufficient velocity, you know, if I throw this, the basketball will begin to fall. Is that right? Now, if I throw it with sufficient velocity such that as the ball begins to fall, the surface of the Earth falls exactly the same amount. Let me see if I can show that to you in a drawing here. Now, this is our Earth. If I throw this basketball with the velocity so that when the basketball falls, you see that as it goes, it is going to fall like this. And you can see here, the basketball has fallen by that amount. And the surface of the Earth at that point also has fallen by the same amount. So, if you can throw this ball with such a speed that the amount of fall of the ball equal to the amount of fall of the surface of the Earth due to the curvature of the Earth, then this ball will never come back to the Earth. It will keep going round and round. In fact, that is what our moon does. The moon is continuously falling towards the Earth. But because it has sufficient speed, the amount of fall of the moon equal to the amount of fall of the surface of the Earth. And therefore, the moon goes round the Earth in an orbit. Now, the question we are trying to answer here is, what is the minimum speed we require so that an object thrown will simply go in an orbit around the Earth? Okay, An object thrown with sufficient speed can be made to go around the Earth in an orbit. You can see here, if this cannon is fired with a low velocity, the ball will come back. But at a particular velocity, the fall of the ball and the fall of the Earth will be the same. And with that velocity, the ball will keep going in an orbit. So the speed needed to keep a satellite in orbit around the Earth is called its orbital speed. And you know how important these concepts are for space travel. Now consider a satellite of mass m placed in an orbit h meter above the surface of the Earth. The distance of the satellite from the Earth will be radius of the Earth plus h. That's no problem there. When the satellite is in a low orbit, we're going to make an approximation here. This h will be very small compared to the radius of the Earth. And therefore, we are now going to say the distance of that satellite from the center of the Earth will be RE. That means when the satellite is placed at a low orbit, not very far from the Earth, the distance of the satellite from the center of the Earth is RE plus h, can be approximated as RE, because compared to the radius of the Earth, the altitude of that satellite is very small. Therefore, we can write an equation now. If m is the mass of the satellite and me is the mass of the Earth, the force of gravity on this satellite can be written as, alright, can you write that equation? What is the force of gravity? Force of gravity is G MEM over RE squared. Well, if you want to make this object to go in a circle, what is the force that keeps an object going round in a circle? The force that keeps an object going round in a circle is called the centripetal force. Do you remember the equation for centripetal force? Centripetal force is mv squared over r, where v is the tangential velocity, or that is what we call the orbital speed. Alright. Now it is this force that provides this centripetal force for the satellite to stay in the orbit. So it is the gravitational force on the satellite that provides the centripetal force that keeps it in the orbit. If v is the speed of the satellite in that orbit, then that centripetal force will be mv squared over re, where re is the radius of the Earth. That means we can now take this quantity, the gravitational force on the satellite, and set it equal to the centripetal force, because this centripetal force is provided by this gravitational force. Let's equate those two equations. mv squared over re equal to g MEM over re squared. Now I have used different colors here. First of all, green colors, m and m will cancel from either side. And do you remember, I told you, I will ask you, we said GME can be replaced by a more familiar quantity. What is GME equal to? Will be small g times RE squared. Let's do that. When you do that,